Yes. Now the next topic is valence shell electron pair repulsion theory, that is also known as VSEPR theory. In this theory, we will be studying about the shape of the molecule, the covalent molecule. This theory was given by Gillespie and Neom in the year 1957. This theory is basically based upon the concept that in a polyatomic molecule, the direction of bonds around the central atom depends on the total number of electron pairs. Now, as we know, in a molecule, two types of electron pairs could be there. It could be the bonding electron pair and it could be non-bonding electron pair. And the shape of the molecule is dependent upon the number of these bonding and non-bonding electron pairs. These electrons try to place themselves as far apart as possible from each other so as to have minimum repulsion among them. So as to gain maximum stability. There are some points for this theory. Let us have a look on the main points of this theory. The very first point is that the electron pairs surrounding the central atom repel each other in such a way so as to gain maximum state. The next point is the geometry or the shape of the molecules depends on the number of electron pairs in the valence shell of the central atom. If the number of electron pairs are, say, 2, let the number of electron pairs be 2. In such a case, the arrangement would be linear. In such a way. The example of such an arrangement is seen in the molecule of BeF2, BeCl2. If the number of electron pairs is 3, arrangement would be trigonal planar, where the electron pairs try to arrange themselves in trigonal manner. so as to have minimum repulsion. Examples are BF3, AL, PL3, etc. And if the number of electron pairs is 4, arrangement would be tetrahedral. In such a way. Examples are CH4, SiF4 and NH4 plus. Further, if the number of electron pairs is 5, the geometry would be trigonal bipyramidal. Examples are PF5, PCl5. If the number is 6, geometry would be octahedral. Now, since the nature of electron pairs in a molecule is different, so the repulsive interaction among these lone pairs and bond pairs would also be different. So the next point of the theory says that the repulsive interaction between lone pair and bond pairs are different from each other. It is as follows. The lone pair interaction or the repulsion would be more comparative to lone pair bond pair repulsion comparative to bond pair repulsion. Next, we move on to the topic of valence bond theory. This theory is also known as orbital concept of bonding. This theory also puts some light on the concept of bonding or the concept of covalent bonding. According to this theory, when two molecules approach each other, according to this theory, when two atoms approach each other to form a molecule, there occurs some decrease in the energy of the system, or else we can say it is accompanied by the decrease of the energy. Let us understand this theory with the help of an example. For this, let us take the example of formation of hydrogen molecule. When two hydrogen atoms, say HA and HB, approach each other, they form the molecule H2, that is hydrogen molecule. As we all know that one electron is present in 1s orbital of each hydrogen atoms. Now what happens when these two hydrogen atoms start approaching each other? During this approach, there is some sort of attractive interaction as well as some repulsive interaction is also there. Now where this attractive interaction is seen and where this repulsive interaction is seen? Attractive interaction or the attractive forces are found in between the outermost electron, say Ea, of first hydrogen or hydrogen labeled as A, and the nucleus of Hb. Similarly, interactive attraction or the attractive interactions are also seen among Eb and nucleus of Ha molecule. Repulsive interactions are seen among Ea, Eb, and nucleus of A and nucleus of B. Since they contain positively charged particles, protons in them. Now due to these two attractive and repulsive interactions, or first of all let us consider the attractive interaction. Due to the attractive interaction, the molecules come closer to each other. And form a molecule. But there is a limit when they approach each other due to the repulsive interactions acting as well. Let us understand this thing with the help of a diagram, say. Let us make a graph for potential energy on one axis and internuclear distance among hydrogen atoms on another axis. When the molecules are at infinite distance from each other, there is no sort of interaction among them. And when they start approaching towards each other, such a graph is seen, which shows that as the internuclear distance is decreasing, the energy is also decreasing. Energy was 0 initially and now it is becoming negative. At some stage when the molecule is being formed and no more overlapping could be done, that particular distance is termed as bond length. This R0 is also known as critical distance. corresponding to minimum energy state. This is the bond length of the molecule. The types of overlapping. As we know that when two atoms approach each other to form a molecule or to form a bond, in such a case their atomic orbitals undergo overlapping. Now this overlap can be of three types. It could be positive overlap, it could be negative overlap, or it could be zero overlapping. What is the meaning of these signs? When we talk about the positive overlapping, it means involvement of overlap of lobes of same sign. That is, it involves overlapping of lobes of same sign. This is the interactive interaction. It results in attraction. Negative interaction is overlap of lobes of opposite signs. And such an interaction is repulsive in nature. Zero overlap means no overlapping. Let us see some examples for these types of overlapping. First is positive overlap. Let us see the overlapping of P Z orbitals. So these two orbitals P Z are overlapping with each other with their lobes having same signs on them with each other. Next overlapping could be for PZ again and S. S is spherical in shape, overlapping having same sign lobes. Next we can see the positive overlapping for the P X orbitals. These are px orbitals. Then signs are the same in this case as well. Then for py orbitals, again the signs are the same in case of the positive overlapping. Example of negative overlapping. As we have seen, negative overlapping is the interaction of lobes of opposite signs with each other. Let us take the example of p z orbital once again. But this time, the lobes which are undergoing overlapping, they are having different signs on them. One is having positive, another one is having negative sign. And such interaction is negative interaction. Same could be seen for sp overlapping involving pz orbital once again with s, having different signs. The upper one is pz, and the lower one is pzs. Now if we look onto the example of zero overlapping, it is seen when, say, px orbital undergoes overlapping with s orbital, which is not possible at all. Similarly, if we talk about the overlapping of, say, px and py orbitals, overlapping is not possible. Such interactions lead to zero overlapping. Actually, there is no interaction at all. Now, as a result of these overlappings, some covalent bonds are being formed. There are two types of covalent bonds which are formed due to these overlapping. The first one is sigma covalent bond. Sigma bond is formed due to the axial overlapping of half-filled atomic orbitals. Sigma bond, it involves end-to-end overlap, or it is also called head-on overlap. In such an overlapping, the electron cloud which is formed, it is cylindrically symmetrical. About the internuclear axis. Now further, this sigma bond could be of three types. First is SS overlap, that results in the formation of a sigma bond, where one s orbital is combining with another s orbital. Second is sp overlap, where s orbital combines with p orbital, as we have already seen. Next is p overlapping, The extent of overlapping is greater in the case of pp overlapping, and that's why the strength of these bonds are in the order pp is greater than ps is greater than ss bond. Another type of bond that is formed is pi bond, represented by this symbol. Now when is this bond formed? It is formed due to the lateral or sidewise overlapping of the atomic orbitals. The overlapping takes place in such a way that the axis of the orbitals